Bless you. All right. So, hello everyone. Let's get going. Notes out. Distractions away. So, with the uptick in quarantines and illness and all that good stuff, just a quick reminder that for this class, to avoid, so like when I post something on Canvas, like if I post an assignment, to avoid confusion for students thinking they have to upload something to it, if you are out and you're working on your homework and you want to submit it to me, I found, and maybe you disagree, we can talk about it if you guys feel it'd be a better way. I'm open to options. What I have found to be the easiest for everyone involved is to take pictures of your work, put it on a Google Doc, send the link to me. Okay. Or an app like Cam Scanner where you can take pictures and it puts it into one PDF file is fine with me. Please stay away from taking 4 different pictures and uploading 4 different pictures to an email and sending it to me that way. Because then I have to download each picture and it takes up space and it's tedious. Like a Google Doc, I click on it. If you share it with me, you guys want to know how to do that? If it's on a Google Doc, like page 1 is one picture, page 2 is the second picture, and so forth. Share the Google Doc. I open it up. It's quick. It's easy for me. Okay. PDF, same thing. I don't have to open 5 pages because it's one PDF with 5 pages in the PDF. Whereas if you attach all those, like I think I told you this before, if I'm grading these at home and I have to like open up 5 different picture files, I don't have home internet. Like we rely on our cell phones as a hotspot. It's a long story. It's terrible. Anyway, I just can't do it. All right, it just takes forever. Versus a Google Doc is a lot faster. All right. I actually, over break, I actually thought we had it figured out. I got like a 5G home internet device, and it worked great for a night. And then the connectivity dropped, and it's no longer connected for the next week. So I had to take it back. Back to the Stone Ages. Anyway, if you could do that, if you are out, if you could do that, email me the attachment of the PDF or insert the link, share the link of the Google Doc with me. And that's just email. That's fine. Do you guys agree that'd probably be easier than the whole Canvas process or no? What's easier for you? Canvas? Oh, Cam Scanner, but like uploading it to Canvas or just emailing it day by day? Uploading it to Canvas is easier? Okay, I'll consider trying that. It kind of depends too, like how many students we have out. Because when it was like we hadn't had anybody out for a while, like it's a lot more work for me to create an assignment where you can upload all the time. And then I have to see that you uploaded it. It's a random person who I wasn't expecting to upload an assignment. Versus if we have a lot of people out, then it might make sense to do it that way. All right. We'll kind of reassess as things go on. Remember, every day's lesson is video recorded, posted every day on the agenda. All right. So feel free to use that as needed. Number 1, on the worksheet, I got L of x is 5/4 x plus 1. I got L of 4.1 is 6.125. I got F of 4.1 is 6.1248. And there's my error listed. Were we close? Where'd we go wrong if we missed it? Did you check it? And if you left your answer as 5/4 times x minus 4 and then plus 6 outside, that's fine too. I think I kind of encouraged you guys to do that yesterday. Help me out. Where'd you go wrong? What do you need help on? All right, I guess we're moving on. Second one, e to the x plus sine of x. Ooh, that's a complicated problem that I wouldn't know how to evaluate by hand. I bet linearization might help. So tangent line, 2x plus 1. Ooh, that's a pretty simple tangent line. Plug in 0.1, I get 1.2. 1.2. F of 0.1 is 1.205004, and my error is 0.005004. Questions on those two? And then which two did I assign in the book? 3 and 4. 3. Shoot, not there. Oh, crud. I don't know why. Where'd 3 go? All right, 3. It looks like L of x was just 2, right? L of x equals 2. Must have had 0 slope. Oh, and I didn't put 4 there. My bad. What'd you guys get for 4 for L of x? How about the tangent line, the equation of the tangent line? L of x equals x? Okay. So questions on that one? All right. Any questions in general on the 4-5 notes? All right, we kind of wrapped up yesterday talking about differentials. All it is a measurement of, it's kind of a difference in the estimated error versus the actual error. We're not going to really get too much into that, maybe later. So this would be your estimated error using the tangent line. But this is the actual, like this would be the actual difference from the true value to the predicted value, right? And so that comes from the actual difference in function height. This is your dx, it's your small change in x. This is your, you have your small change in y, and then your true change in y. So that's another application of derivatives that we're just not going to get into today. I want to make sure we have enough time to get into 4-6. So a little review preview. I want you guys to do this as a warm-up problem. Find the derivative of this implicitly defined function or relation. Some of you probably have flashbacks of me putting a PR on your paper for product rule. Some of you should probably have a red pen with you right now to write PR on your paper. Check it. And a friendly reminder, if you have the same values, just every one of them is off by a sign, positive or negative, every one of the signs is off, it's the same. How are we doing that? That's called implicit differentiation. Why was that ever a thing? Why did we ever have to do that? Nobody? All right. Let's refresh our memories. What's the derivative of this thing? Your half, right? dy dx equals 2x, correct? Now, we're going to get a little existential today because I have to. I even get a little violent with the smartboard. All right. Why is the left side dy dx and the right side 2x? Well, cool. Go for it.
The left side and the right side follow the same rule, but on the right side it uses the chain rule, and the derivative of x is just dx. Dx is 1.
Do you guys hear what he's saying and understand what he's saying? Let's refresh our memories. I really like the way you explained that, Cole. All right. If I did this, okay, and a student who's learning implicit differentiation for the first time, here's probably the way I would explain it, okay? These are both chain rules. This one, I bring the power down, I leave the inside alone, I reduce the power by 1, and I have 2x. Do you all agree? 2x. But I have to multiply times the derivative of the inside. Cole's saying the derivative of the inside is just 1. It's dx dx, right? It's dx dx, which every single time is going to be 1. So do we really need to write it there? No, it's times 1. The left side, it's to leave the inside alone, reduce the power by 1, times the derivative of the inside. But by definition, we're taking the derivative of the y function with respect to x. That's called dy dx. Does that make sense? So what are we talking about here? Well, I don't care if this is y squared equals x squared, m squared, q squared, p squared. You have to be told the variable you're taking the derivative with respect to. Does that make sense? Make me proud. Let's see if you understand. That's a P. What's the first question you should ask me if I give you this problem? And you probably haven't noticed because we get such in the habit of doing it, but any quiz, any homework, what does it always preface it with?
With respect to what variable?
Right. Take the derivative of this thing with respect to, let's do P. Let's do P right now. All right. Okay. Well, that's if it's with respect to P, P is the independent variable. Y depends on p. All right, so 2y dy dx. And what's the derivative of this thing? It's the question you all have to ask between classes, every single period. 2p or not 2p? That is the question, right? Between class periods. Is it worth it? That time? 2p or not 2p? Tough crowd. Okay. What if I say take the derivative with respect to x? Okay. 2, leave the inside alone. Reduce the power by 1. What's the derivative of the inside now? Someone other than Cole. Dom. dp dx. Who's completely lost?
I'm not completely lost. I'm lost in the beginning part. Would the left side for the first part not be dy dp?
Oh, yeah, if I said with respect to p, did I do it wrong the first time?
Yeah.
Okay. Yeah. I was jumping ahead. It's right now. But the previous question I asked, if I said with respect to p, it should have been dy dp, right? Sorry about that. Okay? Everybody okay now? All right. So really, here's what I want you to start thinking of. Okay? I don't write it this way, but isn't this really y is a function of x squared? And if I say with respect to x, that means p is also a dependent variable because p is a function of x. It's really p of, p of x squared. That says p of x. Does that make any sense at all? And so when we take the derivative, you can write dp dx, or here it would be times p prime of x, right? Because p is a function of x. Oh, I can hear it. I can hear the chain rule in that because p is a function of x. It's not the independent variable. So where are we going with this? Well, I want you to hear it, okay? I've given you this example before, kind of alluding to this section. It's called related rates. Related rates. We're all standing hand in hand, maybe not hand in hand, but around a pond, okay? It's very serene until someone throws a rock into the pond. The rock goes into the pond, the ripples go out, and Mason says, I wonder how fast the ripple, the area of the circular ripple is increasing. How fast it is increasing. Well, let's think about it. Ready? Area of a circle depends on what? The circle's radius. Okay. So area of a circle is pi r squared. But Mason says, wait a minute. This circle is not just static. It's not just staying there. It's expanding at a certain rate. Okay. So A is pi r squared, but r is a function of, what's r a function of?
Time.
Time. If I say what's the radius, you would ask the question, well, okay, I threw the rock in. How long have you been watching this ripple go out? How long? And I can tell you its radius if I know the rate it's going out at. Do you agree with that? So area is a function of radius, but radius is a function of time. Do you hear it? Okay? So when I take the derivative of this, am I taking the derivative of A with respect to R? No. What was the question? How fast is the area increasing? How fast? Well, give me some units for how fast. Well, so many square feet per second, square feet per minute, square feet per hour, whatever. Do you hear it? It's with respect to time. So we're going to find dA dt. Help me out. 2 pi r, right? Power rule, 2 pi r. But this derivative is not with respect to r, is it? If it was, we'd be done. It's with respect to time. So what's the derivative of the inside? dr dt. Very good. dr dt. There is your implicit derivative because it's not with respect to a, it's not with respect to r, it's with respect to a variable t because it's an element of time. Okay? Make sense? With that knowledge, we're going to talk about a spherical balloon. This is your first example for today. Air is being pumped into a spherical balloon at a rate of 5 cubic centimeters per minute. Determine the rate at which the radius of the balloon is increasing when the diameter of the balloon is 20 centimeters. All right. Step 1, understand the problem. Can you picture a spherical balloon? It's beautiful. Perfect. All right. Now, here's the way I like to, I guess, write out the given information. I write out a given column, and then once I get to the point where I can hear in the question what it's asking me to find, I'll write that over here. All right. Air is being pumped into a spherical balloon at a rate of 5 cubic centimeters per minute. This is where your job is to take the units and turn them into a calculus notation. Let the units tell you how to write the calculus notation. D blank is 5. Well, 5 cubic centimeters per minute. How should I denote this? dV dt. Perfect. dV dt. It's how fast your volume is changing with respect to time. Just like dy dx is the rate of change of y with respect to x. Let the units tell you what it's measuring. All right, next. Determine the rate at which the radius of the balloon is increasing. Well, that's what they're asking me to find. Determine the rate at which the radius is increasing with respect to time. So dr dt. That's the blank we're going to fill in. Now, just like optimization, the key to the problem is to, you know how in optimization our key was to figure out the constraints and the equation that would optimize the problem? Don't get confused with the two topics, but the approach is similar, okay? When you're doing a related rates problem, you're going to have to identify the equation that relates all the rates. It relates all the rates. Well, this one's easy, okay? It tells you, it gave you the rate of change of volume of a sphere, so you're going to have to use the volume of a sphere formula, okay? And that would be one I would give you, okay? So volume of a sphere is 4/3 pi r cubed. Is that one you guys know, or maybe not? Half and half. Okay, so from a mathematical standpoint, at this point in time, I'm looking at this problem and I'm saying, okay, I'm given a dV dt. I have to find a dr dt. Okay, so this is the equation I'm going to be using. Is there any other information? Oh, when the diameter is 20. Well, I don't see any diameter in this formula, so I'm going to interpret the diameter being 20 as the radius being 10. Very good. So the next piece of information, R is 10. All right, now, spoiler alert, you're going to have to take the derivative of the main equation with respect to time every single time. Take the derivative of the main equation with respect to time. That's the only way you're going to get a dv dt or a dr dt out of this thing. Do you agree? So what is the derivative of this red function with respect to time? Well, what's the derivative of v with respect to time? dv dt. What's the derivative of the right side with respect to time? Well, the 3 comes down. What's 3 times 4/3? 4 pi r squared times the derivative of the inside, which is dr dt. You got it now. Question, Wendy? Did you not see where the dr dt came from? So do you see how this is a power chain rule? The 3 comes down, 3 times 4/3 is 4 pi r squared times the derivative of the inside. Because it's not just r. R is not r. Back in geometry, here's r. Find the area of the circle. Nope. R is a function of time now. It's changing. All right? So it's rt. So the derivative is dr dt. All right, what are we solving for? dr dt. So at this point, you need to make sure, do I have everything else other than dr dt? Do I have my dv dt? Yeah, 5. Do I have r? 10. I can solve for dr dt. Go ahead and do that. Hi. Question?
So we can't find this thing. Like, 3 people looked, nobody could find it.
Which one?
This.
It might have the x's and y's like we did yesterday. It had that one. If the consecutive angles are supplementary, then it's parallel. You don't understand what I just said. Okay, we'll get it in class. I'm sorry, I have to teach right now. All right. All right, we're going to divide by 400 pi. And at this point, what's that? 1 over 80 pi. I would be tempted to maybe leave it like that, unless, I'm trying to picture if that's a reasonable solution. 80 times pi, 80 times like 3.14, 1 over 240th. It's pretty slow, right? Let's write it both ways just to kind of practice both. Did anybody type that in the calculator and get a decimal approximation to the nearest thousand? Lane, what'd you get? 0.0039. And let's go back to the units. All right, what are the appropriate units for this? Well, it's dr dt. So isn't it going to be the units that r is measured in per units of time? So what units would r be measured in? Centimeters, and t is measured in minutes. So centimeters per minute. Pretty slow. Pretty slow. All right, I need you guys to listen very carefully. I'm going to give you a couple warnings, and a couple of things that are helpful as you visualize this, okay? So calculus. Calculus can be confusing because it's the study of changing rates, and we haven't, physics you deal with rates all the time. Earlier math classes, not so much. So here's the problem. Do you remember the red light camera example I gave you very early in the year? Someone drives through a red light camera. The camera takes a picture of their license plate, and it records two things. Because in a picture is static, right? In a picture, you can't tell if their car stalled out in the intersection and it just took a picture of them sitting there, or if they're going through the intersection at 60 miles per hour. Do you agree with that? Okay? So the camera would need to record, okay, the snapshot in time, but also the velocity that's associated with that car. Do you agree? Okay? Same thing for this problem. This balloon is not just staying here at this certain volume. Air is being pumped into the balloon at a certain rate. Here's what I need you guys to get, all right? Watch up here. Spherical balloon. 5 cubic centimeters per minute. But that volume that's being pumped in is constant. That does not mean the balloon is increasing outward at a constant rate. Yep. Let me say that one more time. You need 6 through 28. Alright, I want you guys to get this. Here's a balloon. If I air pump 5 cubic centimeters per minute into this balloon, do you agree from the observer, the 5 cubic centimeters per minute is going to affect a very small balloon? It's going to affect it by a lot early on. It's going to go shh. But then as that balloon grows out, do you agree 5 cubic centimeters per minute? The outward growth of that balloon is going to slow down from the standpoint of the observer. Do you agree with that? That's calculus. Because the radius, here's what the radius is doing. Ready? Let's trace that balloon. Let's trace its radius. Shh. Can you see it? Fast early on, and it slows down. So guess what's happening here? Just like the red light camera, we're taking a picture of the balloon when the radius is 10. Does that mean the balloon stops when the radius is 10? No, but just like the car passing through the intersection, got its picture taken. The car kept going. The balloon, picture is taken. Bless you. But then it keeps going. Make sense? So here's the risk. Here's a bit of a risk when you're doing these problems. Some students will do this. They'll look at this V equation and they'll plug in 10 before any calculus has been done. Guess what that does? If you plug in 10 right here, right now, you're finding the volume of that balloon when it has a radius of 10 centimeters. That's a geometry problem, right? No movement is allowed. That's not what it's asking for. You have to take the derivative to allow this problem to be in motion, because now there's a changing volume with a rate, a changing radius with a rate, and now you can plug in 10 at that instant. Okay? So find the equation, relate them all, take the derivative with respect to time, plug in the unknowns, solve for what you're looking for. All right, let's do another example. A ladder 10 meters long is leaning against a vertical wall with its other end on the ground. The top end of the ladder is sliding down the wall. When the top end is 6 meters from the ground, it is sliding down at 2 meters per second. How fast is the bottom moving away from the wall at this instant? All right, let's draw a picture. We have a wall. We have a ladder. All right, in a lot of these problems, you're going to have to kind of use some logic and some prior experience to label some things. For example, can you see how this is kind of creating an x and y axis, right? So I would probably call this distance up on the wall that the ladder is, I would probably call it y. I'd probably call this distance x. And that will allow you to label some information as they give it to you. All right. A ladder 10 meters long. Well, okay, that, what do you want to call the ladder's, what do you want to call that variable? Now, it's not really a variable because it's not changing in length, but what letter do you want to assign to the length of the ladder?
L.
L, sure. So L is 10. 10 meters. 10 meters. Do you agree that's not changing in length? Anything that's changing in length, you need to kind of keep in your mind it is a changing value. All right? I have to allow it to change. I can't make it static unless it is static all the time. The top end of the ladder is sliding down the wall. I like to do this. I like to put an arrow that tells me that ladder is going down. And what does that mean about the base of the ladder on the ground? It is sliding out to the right. So I'll put an arrow going out and to the right. When the top end is 6 meters from the ground. Question, is the top of the ladder always 6 meters from the ground? No, just at that snapshot in time, y equals 6. It is sliding down at 2 meters per second. Rate. What should we call that? What should we label that measurement as? D, y, d, t. dy, dt, because that tells us how fast the vertical change is happening with respect to time. And we're going to call it it didn't say -2, but because of the way we drew it, and we understand that length is decreasing. When something is decreasing, it has a negative derivative, right? That dy dt needs to be -2, doesn't it? Okay. How fast, here's the question, how fast is the bottom moving away from the wall? That's what we're trying to find. What should we call that? dx dt, very good. Find dx dt. All right, now just like any problem solving, you need to figure out an equation that's going to relate these variables. What's that going to be? Pythagorean theorem. Is it a right triangle? Yeah, it's a right triangle. And it's not dealing with the angles of the triangle. If so, you might have to use Sohn-Cotella, sine, cosine, tangent. If it's dealing with the angles of a right triangle, this is dealing with the sides of a right triangle. The Pythagorean theorem makes sense. Okay? So the equation is going to be x squared plus y squared equals L squared. Am I taking the derivative with respect to x? Am I taking the derivative with respect to y? With respect to L? No, with respect to t. So the derivative of this is going to be 2x times dx dt plus 2y times dy dt equals 2L times dl dt. This is where I stop and I check to make sure I have, because I can only have one unknown. What's my unknown? Because I wrote up here, find dx dt, you agree that's going to be what we're trying to solve for? Right here. Do we have an x? No. Can we find it? Can we find x? Well, at the instant in question, isn't the ladder 10 meters long? Isn't it 6 feet off the ground? And can't I do that Pythagorean theorem to find out in the picture, in that snapshot in time, what the x was? Right? 6 squared plus x squared equals 10 squared. 100 minus 36 is 64. X is what? X is 8. So even though that wasn't given to me, I can find it pretty easily. And this is the point in time where you would just stop and find anything you're missing. Keep going. Do I have a y? Yeah. Do I have a dy dt? Yes. Do I have an L? Do I have a dl dt? Not given, but what's dl dt? 0. How fast is the length of the ladder changing with respect to time? It's not. dl dt is 0. You get it? Look for it. Little preview. You're going to find some problems, maybe in the homework, where a plane is flying at a constant altitude. Constant altitude means dy dt is 0. Follow me? Constant altitude, dy dt is 0. All right, let's solve this quickly. We have 2, and the board's not going to allow me to solve it quickly. 2 times 8 times dx dt. Oh my goodness. This is painful. Sometimes Adobe really slows things down. Trust me, I don't have many tabs open. All right, 2x dx dt, 2 times 8 times plus. It's still doing it. This is painful. All right, 2 times 8 times dx dt plus 2 times 6 times negative 2 equals, what's this whole right side going to be? 0. Solve for dx dt. Okay, subtract, well, dy dt is negative. You're going to actually add those terms over and then divide by 16, and you're going to get your dx dt. Anybody solve that? What'd you get?
3 halves.
3 halves. So dx dt is 3 halves. My gosh. Meters per second. Jen, yes, please help. Send someone fast. 3 halves meters per second. You understand that? These are going to get challenging. Okay? So be patient. All right, the homework for tonight. Just 3 problems. All right, 251, 211, and 13. Let me double check that. All right, two is just an exercise in, you're not actually solving a problem. It's giving you a surface area formula. You're just taking the implicit derivative with respect to time. Okay, you're not actually solving anything after that. 11 is another one of those inflating a balloon problems, similar to what you just did. 13 is one of those I was talking about. Watch up here. An airplane is flying at a constant altitude. and you're asked to find what is the speed of the airplane at that moment. So you're looking for the horizontal rate. Just a hint to you, the vertical change, dy dt, is going to be 0. All right? Have a wonderful day.